Okay, so I am back here looking at Lagrange points again. So let me just give you a recap of where we are so far. So a Lagrange point is, suppose I have these two masses that are orbiting each other, and I made it so that they were different enough masses so they orbit a common center mass. There are locations, there's 5 locations around here where you can put another low mass object and it will have the same angular velocity as these two. So it'll stay in the same position relative to that. And those are the Lagrange points. So L1 is right here. So here's a large object, here's a small object like the Earth and the Sun, and they're orbiting. And then that point right there will stay relative to it. So how does that work? Well, if you put a mass right here, there'll be a gravitational force pulling it this way due to the large object. There's also a quote, backwards pulling force due to this interaction. The sum of those forces is the exact amount to have it move in a circular orbit around this center mass with a angular velocity that's the same as these two. So from that, I had to find the initial conditions for stable circular orbits for this binary star system, or masses, whatever you want to call it. So if I start off with mass m1 and m2 separated by distance r, and then from there I calculate everything. So I find the center mass, I find the initial velocities for these things to rotate, and then I have that. Then what I want to do is to calculate the force on a mass at this point due to this, and so you notice that it's further away than that one, but they're pulling in different directions. So I have the gravitational force due to m1, the gravitational force due to m2, and then that would be equal to mass times acceleration. And the acceleration is due to us moving in a circle of radius r L1, which is the orbital radius. And this equation is not easy to solve. I solve it, and then I made a better way to solve it, and now I'm going to make an even better way to solve it. So the key here is that I'm going to smash this down into a one-dimensional problem and treat it like a mass on a spring, kind of like. Okay. So it turns out that, and I'll plot this, but if I put a mass, the problem is that this is an unstable equilibrium point. So if you're a little bit off in your calculation, then it won't stay there. But if it's exactly right, it will. But it's kind of hard to find that exact value with this complicated equation. So I made a better method, and I think it worked fairly well. Also, the further apart these are, the more stable it is. So what I want to do is to put a mass in one dimension, and I will have 3 forces acting on it. So let's do that. So let's say I have a mass in the x direction. So here's my x-axis, that's the origin. Here's m1, here's m2. So I know the locations of those. And then I'm going to put another mass right here. And this is called that m. So there'll be f1, and let's just put this as scalars. And then I'll have f2. And of course, if that was it, then it wouldn't be that interesting a problem. What I'm going to do is add in the fake centrifugal force. So remember that if I have this equation, F net equals ma. So that's Newton's second law. If I want to have a non-inertial reference frame, an accelerating reference frame, I can take this mass times acceleration and treat it like a force. So I'll have F fake is equal, that's the acceleration of the reference frame, is equal to negative ma frame. So in this case, the reference frame is going to have an acceleration of a centripetal acceleration, a frame, of omega squared r. So let's call this r. Let's call that the r direction. So that means that it would have an acceleration this way, so there'd be F centrifugal force pointing that way. So I have those 3 forces, and I can let it move about. But it won't find the equilibrium position. Even if it did, it'd pass right through it. What I want to, again, add one more force is a drag force. So I'll just say F drag is equal to K. Actually, I'm going to use KD for drag. Negative KD times the momentum. And I should make these all vectors. But, so that means that it will kind of settle down as long as there's a motion, there'll be this drag force, but once it gets to an equilibrium point, it'll stop. Okay, now there's going to be a problem because if you plotted this like a hill, so if you look at potential as a function of r, it's going to look like, with including this centrifugal force, it's going to be unstable like this. So if I put an object right there, it's going to stay, but if I put it right here, it's going to go that way. If I put it right here, it's going to go that way. So what I can do to fix this problem is to calculate the gravitational force due to each of these, and then just flip the sign. So that will kind of make this look like that. And now it will settle down to some, hopefully, equilibrium point right there. And it will settle down because it has that drag force. Okay, that's a lot there. Okay, well, let's just get to it. I'm going to start with my old program and start deleting stuff so that we can get the same values. And I can compare what value I had before. Actually, I'm going to run this and write down the number because I'll forget. So let's switch over to the computer. This is the exact same program. I just copied it. And I calculated the Lagrange point right here, and I did an iterative calculation. So I calculated the left-hand side and the right-hand side until the left-hand side was less than, and then I went back a step and did it with a smaller step size, and I got this. And that gave me this value right here. Let's just copy that. I want to write that down. Let's see. I'm going to write it down over here because I'll forget it. So 1.482278655 times 10 to the 11th. And so you have to do in Python, I'm using GlowScript. Python, GlowScript v Python. You have to actually tell it to print more digits than what it would normally do, and it did. Okay, let's start deleting some stuff because I want the same masses. I want the same R. I want all that stuff. I want the stars. I don't want this defined. I don't want to do that. Let's just get rid of that. I know it's no fun to, and then I don't need to do this. I don't need to do all that stuff. Just make it clearer. And let's just put R, print RLS. I don't even know what that is. R new. So I'm going to just go ahead and put R new. That's the old value. Actually, I'm going to put, actually, that's what I should do. Let's see if I can undo. Okay, I'm going to go back and put that original function in there. This one. Let's see, I'm going to copy it. I deleted it. Okay, so this calculates the Lagrange point with R, M1, M2, the starting position and the initial and the step size. So let's just do R new equals L1 R M1. Is that right? M1 M2. The start will be 0. That was my original way. I started at R equals 0 and moved up until they were less. And then I could say this is R divided by 1,000. So that's a pretty bad answer, but that's going to start it. And then it's going to have a position there. I can give it a mass. I can give it a momentum. And then everything down here, it should work for modeling the motion of it. And let's just run that just to make sure everything's working okay. Okay, that's right. And it shouldn't be super stable. Yeah, now it's getting offline. Okay, excellent. Okay, so now, but what I want to do is to, first of all, I'm going to fix my stars. My stars can't move. So down here, this is my loop that does a numerical calculation on all that stuff. I don't want the stars to change momentum, so I'm just gonna put that at star. Actually, I don't really care if they change momentum. I just don't want them to change position. So down here, the stars aren't gonna move. And then on top of that, I'm gonna make the ball start with a 0 momentum. Ball.p, so let's put this at 0. So it's gonna, my ball is the object I'm gonna put near the Lagrange point, and I have those two forces acting on it, and that's it. Let's just run it and see what happens. Yeah, okay. So something crazy. So let's go ahead and make a graph. Did I already have a graph in here? I thought I did. Graph. Okay, I'll put a graph, because I don't really care about the motion. I do care about the graph. Okay, so let's say G1 equals, is this big enough? I think so. It's graph. X title equals I guess R, and then the net force maybe on the top. And so let's say X tidal is R in meters, and then Y tidal is equal to F net in newtons. So that we'll know where the F net is 0, that's where we want to end up. That makes sense? And then F1 equals G curve color equals color dot blue. And then down here, let's go ahead. Okay, so that's my F. That is my gravitational force in between the two stars. That makes the two stars orbit. I don't really care about that. F1 is the gravitational force due to the star 1 on the ball. F2 is due to star 2 on the ball. So I need to add in there my angular velocity, in which I do have omega up here. Yeah, omega. So I can calculate my fake force. I'll call it Fc is going to be equal to positive. Let's see. So it's going to be m ball dot m times omega squared r. Now, so r is going to be equal to ball dot pos. Yeah, that's going to work because ball dot pos is in the x direction. So that's kind of a weird way to do it, but it's fine. And then this is just going to be, I already said I'm going to do negative F1 minus F2 plus Fc. So that means I change the direction of those two forces, two gravitational forces, and I don't have the drag force in there yet. So I kind of feel like I want to do position versus time. Let's do that. Let's do position versus time. Let's do this. I'm going to leave off the units because I'm going to change this up. So let's just put this as T, and then let's put this as R. Okay, and then down here, I can move everything, and I'm going to say F1 dot plot T ball dot POS dot X in the X direction. Okay, I know this is a little messed up, but let's just see what happens. Okay, so it does oscillate back and forth. I wrote down here 4.88 times 10 to the 11th, 4.88. So it's down here somewhere is the equilibrium position, but it's oscillating back and forth between those. Okay, so let's add in our drag force. So I'm going to go down here and I'm going to say, let's say KD equals, I'm just going to pick a value 1. And then the net force is going to be also equal to minus KD times ball dot P. So that's we could do a better model for drag force, but it doesn't matter. I just want it to stop. Okay, let's put that in there and see what happens. KD, edit. Did I put it as K? K2. Why did I put K2? KD. Okay, something bad happened. I think my drag force may be too much. So let's put KD at 1 times 10 to the negative 3. Yeah. Okay, so that's a little bit too much too. It's kind of moving at a constant speed. So let's put this at 10 to the negative 5. Try that. 10 to the negative 6. I'm going to go big, go small, or go home, right? That's what they say. Okay, there you go. So I like that, right? Because it's oscillating back and forth and gets to some equilibrium position. Let's print that thing out after the loop is done. And it's running for a long time. Oops, dt. So let's print R1 equals ball.pos.x meters. Okay, so it's got to let it run its course, settling in. I shouldn't have let it run that long. That does look pretty good, though. I like that. I think it's at something good. I don't know why, but I just ran it. Okay, I think it's done. So now we have here 1.49. So that's a little bit high. That's kind of interesting. I wonder if it's still oscillating. I just can't see it. Let's try. What if I have, should that make a larger drag coefficient? Let's try larger, maybe really get to stop. So let's make that a little bit larger, and let's just see what happens. I should have remembered that number, but I forgot already. So let's say 1 times 10 to the negative fifth. So a higher drag. Oh, it settled right to it. Now maybe it got stuck, right? And it's kind of slowly moving down there, and I can't even really see it. And so I don't know that this is a good idea. I kind of want it to oscillate more, so maybe less drag. Because I can see it kind of like very slowly approaching that best value, but the drag's too high, so it's just moving so infinitesimally slow that it's painstaking. So yeah, so let's try it a little bit lower. Let's try -7. Oh, I did 6. Okay, so 4.8. See, it's not, because I have 4.822. I don't know why it's getting too large. It's settling in on too large of a value. It should be down here. I wonder why. It's still oscillating, though. That's kind of interesting. Okay, let's do this. Let's plot. Let's plot the energy as a function of distance, because the thing's moving back and forth, right? So it should be at the point where the potential energy is the lowest in this particular case, or at least in equilibrium, even a maximum. Let's actually print the real potential. So that's going to be the gravitational potential energy due to star 1, the gravitational potential energy due to star 2, and the centrifugal potential. So if you integrate that centrifugal force with respect to R, then you get a centrifugal potential. I know that's silly, but would that be positive or negative? Let's see. I'm not 100% sure. Let's see. Wait 1 second. I did this. I'm just checking the way I did it before. Negative. Let's see. Negative. Ball.m omega squared plus. Oh, I have plus k d times. Oh, okay, that's what I did. I switched the, I think it's the same thing. I just switched the orders of stuff. Okay, I'm not too happy with this, but let's see. Let's just carry on. Let's plot the energy. Okay, so going down here, I'm going to change my graph to R and E. And then down here, I'm going to have, let's relabel this FU1, FU2. Let's just plot the total. Let's just plot this as FE. Or let's leave it as F1. Okay, so down here, before I plot stuff, I need to calculate things. So I'm going to need, the total energy is going to be the gravitational potential energy 1, U1 equals negative G times ball.m times R is the distance, no, that's not it, R1B times M1 divided by mag R1B minus, that's U1. U2 equals the same thing, negative G times ball.m times M2 divided by mag. So you got to do that again. Mag of R2B, R2B. That's the two gravitational potential. I need the kinetic energy. Do I need that? Let's just plot the potential. And then UC is going to be equal to, what did I write that down as? I wrote that down as 1/2, so 0.5 times ball.m times omega squared, and I'm assuming omega is constant, omega squared times the position squared, r squared, so it'd be times ball.pos dot x squared. And then we're going to plot ball.pos.x and u1 plus u2 plus uc. I don't know how this is going to work. Oh, that's kind of cool. And so this point is still working. It's still going back and forth. And that shows that it is this hill. And it also shows something interesting in that it's a lopsided hill, right? It's not stable the same ways. And I didn't even realize that. So that's kind of cool. This point right here is somewhere around there. Is going to be 1.5 times 10 to the 11th. I had 1.48, which is, it's not plotting that very well. I wonder if I can do a log plot in the x direction. Let's do this. Graph 1. Graph. Let's try this. I think it's log x equals true. Is that log? 4.1858. So that's a 3. No. That does not look like a log. That would give us a better answer. So, I don't know. I think I need to work on this a little bit more. I think this method isn't really giving me as good of a value as before. I think what I'd like to do is investigate the stability of point L1 by just using a whole bunch of balls. I think that's what I'm going to do next. So I'm going to stop here. I'll give you the code to this. I'll put this in my list of Lagrange point playlist, which I'm just having fun with this. I'm going to do L1, look at the stability of L1. Actually, I'm going to move over to L2. I'm going to switch over to L2, do the stability of L2 with a bunch of masses all right by there and see how they evolve with space. And then I'm going to go look at Lagrange points 4 and 5. 3 is on the other side of the sun. I'm not really too interested in that one, but we'll do that one eventually. So there you go. There is my Lagrange point video for you. I'll talk to you later.